When I'm planning an event, it's tempting to dive into details, like which appetizers to serve and how many. But before that, you need to know the big picture. Who are we inviting and how many guests are likely to come? Without that information, planning the small stuff just doesn't make sense. Acid-base chemistry works the same way. It's easy to get lost in the details with so many species and reactions. But first, step back and consider the big picture. Identify which species are present in large amounts. These are your majority species. Once you know these and their concentrations, you can focus on the smaller details, like the concentrations of the minority species. Just like planning an event starts with figuring out the guest list, analyzing acid-base mixtures starts with identifying the majority species. This leads to a two-phase approach. First, we zoom out and take stock of what's present in large amounts. These majority species set the stage for everything else. The good news? There aren't that many possibilities. Only certain combinations of species can coexist in significant concentrations, and that makes things much simpler. When we move to phase 2, figuring out the concentrations of the minority species, we'll only have to consider a small set of possible outcomes from phase 1. To keep things simple, we'll focus on monoprotic acids and bases, those with just one labile proton that can be transferred. And we're only going to consider the 4 chemical species that are active in acid-base chemistry, the species that participate in proton transfer reactions. From strong acids and bases, we have hydronium and hydroxide ions. Weak acid-base chemistry adds 2 more, the weak acid, HA, and its conjugate base, A-. These 4 species drive the proton transfer reactions we'll be analyzing. When we're giving a mixture of any of these species, our job in phase 1 is to figure out which ones will be present in large amounts when the system reaches equilibrium. That means identifying the majority species in the mixture. So what might we find when our phase 1 analysis is complete? We might find that only 1 species is present in large amounts. If hydronium ion is the only majority species, we have a solution of a strong acid. If hydroxide is the only majority species, it's a solution of a strong base. Or maybe the only majority species is HA, meaning a weak acid solution, or just A-, meaning a weak base solution. That's great, but things can get a little more interesting. We might also find a combination of majority species. But here's the thing, there aren't that many possibilities. Only certain species can coexist peacefully in large concentrations. In fact, at most, only 2 of our species can be majority species at the same time. And there's only 3 such pairs. This is our phase 2 reasoning. One of these pairs involves hydronium ions. Hydronium is a water molecule with an extra proton that it doesn't really want to keep. It will donate it to any species that can accept it. The only one that can't accept it is our conjugate acid HA, because HA already has a proton and has no room for another one. So hydronium and HA get along just fine, making them our first compatible pair. Since hydronium ion is a majority species, we immediately know the pH. Our next pair involves hydroxide ion. Hydroxide is a water molecule that has lost a proton and really wants it back. It will steal a proton from any species that has one to give. The only species that doesn't have one to give is the conjugate base, A-. So hydroxide and A- also get along well. They form our second compatible pair. In this situation, because hydroxide is the majority species, we immediately know the pOH, and thus the pH. Our third and final pair is HA and A-, our weak acid and its conjugate base. It's not that they don't react with one another, they do. In fact, they're constantly undergoing proton transfer with each other. But this reaction doesn't change the overall number of HA and A- molecules. It's just like they're playing catch with the proton. That's why they can coexist in large concentrations, making them our third and final compatible pair. In this situation, we use the Henderson-Hasselbalch equation to determine the pH. And that's it. After phase 1, these are the only stable mixtures we can have. That means phase 2 isn't so bad. We just figure out how to determine the concentrations of the minority species for each of these cases, and thus the overall pH. Now that we have done that, we can tackle any acid-base problem that comes our way. Just like planning an event starts with figuring out the guest list, analyzing acid-base mixtures starts with identifying the majority species. This leads to a two-phase approach. First, we zoom out and take stock of what's present in large amounts. These majority species set the stage for everything else. The good news, there aren't that many possibilities. Only certain combinations of species can coexist in significant concentrations. And that makes things much simpler. When we move to phase 2, figuring out the concentrations of the minority species, we'll only have to consider a small set of possible outcomes from phase 1.